Hello! Hi all, I'm Old Brother. Today, we'll discuss cost superconductors. On July 22nd this year, a team from the Korea Quantum Energy Research Center unexpectedly published a paper online and shared two videos claiming they made the world's first room temperature and atmospheric pressure superconductor. When this paper came out, it immediately set the internet on fire. What is a room temperature and atmospheric pressure superconductor? Simply put, it's something that can transmit electrical current without any loss at room temperature and atmospheric pressure, meaning the electrical resistance is zero. It doesn't sound very impressive, but there's one indicator that can show how significant this is. This room temperature superconductor is referred to as the Holy Grail in physics. Everyone in the field of physics wants to achieve it, but no one has been able to do so. It can only be classified as science fiction. It's sci-fi. Right now there are a few holy grails in physics and we've discussed them. Everyone try to grasp what they are, like dark matter and dark energy, which are the holy grails of physics. What's even more impressive is the unification theory combining general relativity and quantum mechanics, known as string theory. These are all the holy grails of physics, and this person is at that level even if his name doesn't sound that impressive. In a previous episode, we talked about classifying cosmic civilizations. Earth is currently at level 0.72, not even reaching level 1. If a room temperature superconductor is discovered, we would leap to the next level. It's that impressive. Civilization instantly advances by one level, so when the Korean team announced this, everyone said, wow, definitely a Nobel Prize. If it's something as extraordinary as this, the paper would definitely make waves once it's published. However, I noticed that most mainstream media didn't report on this immediately because the Korean paper was posted on a site called Archive. This site is specifically for collecting preprint versions of papers. A preprint is a version of a paper before its official version, much like a draft. Yes, it's an informal version of the paper that anyone can post. Its primary purpose is to establish a claim, in the event that you have made a significant discovery, right? You promptly put a draft up there. Oh, because writing a paper takes time, right? If it gets controversial later, that's not good, right? If someone like Ramanujan appears, your heart would be broken. Yes. If suddenly someone comes up with the same idea, wouldn't you be in trouble? Also, because it's a preprint, it means the paper hasn't been reviewed or certified by a third party. So, whether the content of this paper is true or false is unknown. Oh, are there individuals boasting on this particular website? Yes, practically every single month. People often boast about things, and later it's discovered that they are incorrect. But it's okay to discuss and research, right? It's like finding dark matter. People take a glance and then move on, don't they? So, initially, mainstream media reported on this matter, but the real coverage by the mainstream media came at the end of July, particularly on August 1st, in the most authoritative scientific journal. A columnist from the Royal Society of Chemistry, Derek Lowe, wrote an article. The article was quite lengthy, and he concluded by saying, I think this could be the most credible room temperature superconductor yet, and I'm eager to see future developments. Once this top magazine mentioned it, the media began covering it. He gave several reasons for this claim. First, both the Shenyang National Lab for Materials Science at the Institute of Metal Research, Chinese Academy of Sciences, and the Lawrence Berkeley National Lab in the US, through computer simulations, believe the superconducting plan by the Korean team is doable. It is possible. Secondly, the Korean team published a paper in which the synthesis method described is relatively simple. In the past, many claimed they made this superconductor, but it turned out false. Those fake papers share one trait. The synthesis method is super complex, making it hard to check if it's right or wrong. However, this one is written simply, showing confidence that anyone can easily replicate and verify it, making it seem real. Thirdly, just 2 hours after this paper was published, another paper with the same content came out, and the authors of these papers are different. The first paper has 3 authors, and the second paper has 6 authors with some overlap. What does this indicate? It suggests that there is internal conflict within the Korean team. Why is that? This indicates it's true. Everyone is vying for this success. Aren't there duplicates? There are 2 duplicates, and the rest are competing among themselves. The Nobel Prize can only be given to up to 3 people for one research achievement.
If others have taken the spot, they won't.
Alright, but if you can prove that the person inside is not real, or has no connection with him, you still have a chance. After publishing 2 articles, you can see their internal conflict, revealing what's real and fake. How could it be set up like this? Yes!
It's not about caring so much about these external things like the Nobel Prize.
You can only receive it once in a lifetime, right? It's awarded to just 3 people, so even if 6 are nominated, only 3 can get it. Yes, that's the rule. No exceptions.
Once these 6 might again.
Let's study who contributed more and who contributed less. That's how it is, and those 2 people definitely exist, right? I will explain why these 2 people are so important in a moment. Now, before we specifically introduce room temperature superconductors, let's first explain what a superconductor is. A superconductor, as the name suggests, is a material that can conduct electricity extremely well under certain conditions. How super is it? It means zero resistance, none at all, and it conducts electricity with zero loss. Now the wires we use are copper, which is quite conductive, but they still have resistance. The longer the distance, the more the electrical loss. This loss mainly shows up as heat, and it gets serious, especially in ultra-long-distance power transmission. Power can be lost over a few hundred kilometers, suddenly leaving no electricity. The electricity we use comes from power plants, so the distance between the plant and the user is crucial. If a country is large, it must build plants in various spots. Otherwise, electricity can't reach those areas. But with superconductors, no matter the distance, resistance is zero and loss is zero. You can build a power plant in the best spot, and the whole world can use it, giving the entire country a winning vibe. Plus, with no transmission loss, we can better use some clean energy sources. For instance, wind and solar energy can only be set up in limited spots like deserts or offshore areas, which are usually uninhabited. The farther they transmit, the more the loss, and they don't generate much energy initially. If the loss is too high, it's inefficient, but with superconductors, it's feasible. This superconductor can be used not only in geographical transmission, but also in energy storage batteries, removing loss. Currently, an unused battery eventually loses power, which is a form of loss. If we use superconductors for batteries, they'd always keep power. The electricity amount stays constant. You could leave a battery for a century without problems, and it wouldn't degrade. Also, when using phones, they heat up, causing energy loss, and the battery depletes fast. With superconductor batteries, the electricity amount would remain constant, allowing full usage. The same applies to electric cars. Current ones heat up and lose energy, limiting range. With superconductors, much longer distances are easily achievable. Without energy loss, the battery's lifespan would greatly extend. Once you make a battery, it's like charging it, and it can be used forever without ever breaking. So, how would people make money? Well, there wouldn't be this kind of consumption, so people wouldn't need to spend money on this. Of course, some people who make money from batteries might not earn as much, but the direction is correct. If the number of batteries decreases, environmental pollution would also be reduced. Superconductors are ideal for power systems. They would make the power system perfect, which is why scientists globally research them. In daily life, many things conduct electricity, and among them, the wheel has the best conductivity. Second is copper, third is gold, and conductivity of aluminum, tungsten, nickel, iron, and silver. Aluminum is 63 times 10 to the 6th power Siemens per meter. The second place, copper, is 59. The larger the number, the better the conductivity. Gold is 45. These are all very conductive materials. So if silver conducts electricity better than copper, why don't we use silver for wires? Because it's too expensive. Now, what is the conductivity of a superconductor? This 63 is the highest, so what about a superconductor? Is it 100? No, it isn't. Infinity. You are aware of the kind of vast magnitude it represents, correct?
It is not simply a number, it is something derived from the natural world. It was quite stringent.
Actually, it is a very ordinary thing, but under certain special circumstances, it becomes a superconductor. Well, more than 100 years ago in 1911, the famous Dutch physicist Heike Kamerlingh Onnes was studying the properties of materials at absolute zero. Mercury, or quicksilver, was suddenly found to lose its electrical resistance when the temperature nears absolute zero. Really? So the discovery of superconductivity was made, and thanks to this discovery with mercury, Onnes received the Nobel Prize in Physics in 1913, just 2 years later. Later it was found that aluminum, tin, and lead also have this trait. Aren't they common materials? However, they need cooling to near absolute zero. Superconductors were discovered over 100 years ago, and many more have been found since. The issue is that current superconductors need extremely low temperatures, sometimes near absolute zero, to show superconductivity. It is very difficult to cool anything down to near absolute zero, which severely limits its application. Therefore, scientists later shifted their focus to another question. Is there a material that can exhibit superconductivity at a higher temperature? It turns out there is. More than 70 years after Onnes discovered this superconductivity phenomenon, in 1986, a German physicist at the IBM Research Institute in Switzerland, Johannes Bednorz and Swiss physicist Alex Müller found a ceramic material in the perovskite family that shows superconducting properties at minus 196 degrees Celsius, the temperature of liquid nitrogen.
Near absolute zero.
It's a bit higher by a few dozen degrees, and since liquid nitrogen is easy to make, this cuts the production cost of this superconductor. The potential for use has also greatly risen, marking a big breakthrough in superconductivity. The two scientists received the 1987 Nobel Prize in Physics just a year after this discovery. From this answer, you can see, right? Most physicists wait decades for a Nobel Prize, and some wait a lifetime. Einstein discovered the photoelectric effect and waited over 10 years for the Nobel Prize. It was to verify if his results were correct and how significant his contribution was. This doesn't happen immediately. Just saying, if this Korean team's claim holds, they directly showed it to others.
It really needs to be sorted out, doesn't it? The 3 sent earlier didn't tell anyone. They quietly did it themselves.
Yes, it was sent out. Exactly. That's the characteristic of the situation. You don't have time to discuss it with others.
Yes, they just sent it out. It should be that both times were included.
Perhaps it was dispatched by another individual, not just those two. I believe he sent it out due to his concern about being excluded. He included those two and sent it early. Later, when others noticed, they wondered how it was sent, quickly organized, and sent another saying, this is the official version. Even though minus 196 degrees is still very low, in superconductivity, it's seen as high. Most materials need to be near absolute zero for superconductivity. So when this was found in 1986, it was called a high-temperature superconductor. Though the temperature isn't very high, what happened after finding high-temperature superconductors? Even with improved environments and scenarios for their use, everyone knows this isn't a temperature we face daily. So even high-temperature superconductors are seldom used in real life. Using liquid nitrogen in your phone, computer, or any device isn't practical. Plus, you'd need to keep refilling it. In the future, needing to charge your phone and add liquid nitrogen would be pointless. Since 1986, scientists in superconductivity have been exploring materials that might be superconductive at room temperature. Right? That's the real application. So far, the highest temperature in high-temperature superconductors is in a mercury, barium, calcium, copper oxide material with a superconducting temperature of minus 140 degrees Celsius. It is also extremely low. Well, aside from this particular instance, the significant news prior to that was 3 years ago in 2020, when it was officially published in Nature magazine. The joint research team from the University of Rochester and Intel Corporation's University of Nevada published a paper stating that carbonaceous hydrogen sulfide exhibits superconductivity at room temperature of 15 degrees. However, it is unfortunate that although this superconductor does not have high temperature requirements, it demands extremely high pressure. What kind of pressure is needed? It's called 267 GPa, which is 2.67 million times the standard atmospheric pressure. This pressure is almost similar to the pressure inside the Earth's core, which is currently believed to be around 300 GPa. This room temperature superconductor requires very high pressure.
Yes, it uses extreme force to achieve pressure greater than the Earth's crust. This is the pressure we're talking about.
There are also 2 diamond tips, right, pressing together to compress that gas. Oh my, with such immense pressure in Asia, your superconductor is quite minuscule, isn't it? Just a little bit, yet it is superconducting. Just a little 1.7 points, completely compressing the gas until there's nothing left. 2 diamond tips. Diamonds aren't afraid, right? They're particularly hard. Are diamonds at home?
So big.
The pressure's correct, it can't crush, you know diamonds have.
How impressive! But can the extent of diamonds be investigated?
It's possible, so once clear, it might break or be challenging. All research so far points to one conclusion. To achieve superconductivity, either at very low temperatures or under very high pressure, you must choose one or experience both. Everyone can appreciate the impact of the video released by the Korean team on July 22nd. There's this object floating above the magnet, and they're using a stick to push it. From this video, you can immediately tell that this is likely at room temperature and pressure. Under such extreme conditions, you might observe something resembling white mist due to the intense cold, or you might not perceive anything at all because it's under exceedingly high atmospheric pressure. You observe the Korean team prodding it with a pen, and that's quite intimidating, but I didn't notice anyone present there.
How can it be proven that it's a human hand? There's a hand showing.
That's right. Robotic fingers. Well, I honestly do not know either. So later on, they mentioned that there are too few of these 6 in Korea, but the implication for Korea is that it's quite favorable, right? It's really that straightforward, he mentioned.
Is it conductive?
Did he? Has he got a paper with charts showing they measured this electromagnetic type? It's superconducting. A very distinct feature of this superconductor is that it can float above a magnet. Oh, that's the thing. Yes, this magnetic levitation phenomenon occurs due to 2 effects. One is called the Meissner effect, and the other is quantum locking. These 2 effects work together to make it float in place. This type of magnetic levitation is formed by mutual repulsion with the magnet, which is different from simple magnetic repulsion. In fact, magnets repelling each other cannot float. You can try it and see. When you repel 2 magnets, they just come close to each other. Certainly, there is a repulsive force present, but once you release it, it either flies away or flips over and sticks together. It cannot simply float. The levitation of a superconductor doesn't have this problem because a superconductor doesn't have north or south poles. It repels the magnet on any side. So it's not because of the alignment of its poles. It's because it cannot pass through the magnetic field lines, causing the field lines to form around it.
Is there any other object or material that can produce this type of upward thrust and levitation effect besides magnets?
It's just that only magnets have magnetic field lines, right? It's normal not to understand. Moreover, it has another feature, which is that it won't be bounced away. This magnetic levitation is mutually locked. It's as though there's an unseen force maintaining its position, keeping it elevated in the air, so even if you move it over, it will not fall.
Magnet,
Flip it over, and even upside down, the magnet won't fall. They cling to each other, and if you hold this magnet, it can float without trouble. They're tightly locked together.
Record a video. Yeah, just saying this video isn't enough.
We haven't seen so many phenomena. This is called quantum locking, Tian and Phaeton.
Yes.
This is how the missile really is. So the traits of this locking can be: it can be utilized on maglev trains as well as missiles. If the maglev train is equipped with repelling poles, it creates levitation, which makes it prone to derailing. If it goes fast, wouldn't it derail? Normally, it would derail or flip over, right? But this one won't lock you into the track's shape. It just runs along the track and won't leave it. The distance remains consistent, and there won't be any friction. Even if the train tips over, it can still run. Haha, there is absolutely no problem at all.
Allow me to view that video once more. I have a feeling that a portion of it is connected.
This is called semi-levitation. This semi-levitation is probably not caused by the object being too large or too heavy. If you cut it in half, it might still be semi-suspended, showing diamagnetism, a trait of superconductors. But not all diamagnetic things are superconductors. Some aren't. The key to superconductors is zero resistance. Suspension is just a sign. The paper claims zero resistance was measured, so you might think it's a superconductor. That's the impression from the paper. The Korean paper says the superconducting material they made is called LK-99. The L and K are the initials of the names of two people mentioned in these two papers, one with the last name Lee and the other Kim. The 99 refers to the year, as this material was actually discovered in 1999. After over 20 years of checking, they think it's real, so they named it LK-99. Its chemical formula includes lead, copper, phosphate, and oxide. What's its superconducting temperature? An amazing 127 degrees. It means that as long as it is below 127 degrees Celsius at one standard atmosphere, it is a superconductor. Let me ask you, even at 100 degrees Celsius, it is still a superconductor, unlike those that must be cooled to several hundred degrees below zero. Yes, as long as it is below this temperature, it works. Moreover, the Korean team says that making this material is very simple. By mixing lead sulfate and copper phosphide together and heating them, you can obtain it. Lead sulfate and copper phosphide are cheap, common in many factories. While not easily accessible daily, they're widely used industrially. So, making this material isn't hard and needs no special environment, just some heating. This production method has amazed scientists globally. Until now, all superconductors needed special environments for production, but Korean scientists say just mixing these two and heating works. This is the most incredible aspect theoretically. Why do I say this? It's because why some materials become superconductors under low temperatures or high pressures isn't fully understood now. While numerous theories attempt to explain it, none comprehensively cover all superconducting phenomena. However, all superconductors exhibit one common characteristic. They exist either at low temperatures or under high pressure. Both of these conditions involve a reduction in the material's volume. When metals cool, they contract, and gases under high pressure also contract. So, it seems reducing volume is key to forming a superconductor. If so, a superconductor at normal temperature and pressure seems nearly impossible. How can you reduce volume under normal conditions? Thus, the room temperature and pressure superconductor by the Korean team must be formed by a completely different mechanism from current superconductors. It doesn't need to reduce its volume, or it has essentially reduced its volume in ways we cannot see. What does that mean? The Korean team thinks it's the second option. They mixed lead sulfate with copper phosphide, right? After these reacted, the product's volume decreased, which is like reducing volume, right? But after calculating, they saw the volume only shrank by 0.48%, so this option seems unlikely. So what's the principle? They don't know. Also starting from the 1990s. It just keeps going. Some claim they found this room temperature differential pressure superconductor. Even before the Korean team, some had discovered a similar substance, claiming it was a room temperature differential pressure superconductor, very similar. Did that person publish it? Yes, they did, but later no one else could synthesize that substance to form a superconductor, so it was considered fake. Or maybe it can't be reproduced. How about this? Yes. So are you currently researching if it can really be replicated? And indeed, there are definitely people online. However, at present, the online attempts are not 100% successful. We've tried many times, and occasionally it works, but it feels like a matter of luck.
Possibly.
Success rate's low, and others made results like the Korean teams, with everything semi-suspended. Everyone's like that, but here, I want to mention a conclusion so far. The paper's been out for over 20 days, and research institutes in various countries have done experiments. Also, Hwajong University of Science and Technology has indeed made a semi-levitating material like the Korean teams. In other words, there's a material with diamagnetic properties. Unfortunately, except for the Korean team's claims, materials made by other teams don't show zero resistance at room temperature. Not a superconductor. The sample from Southeast University, China shows zero resistance, but the temperature must be under -163 K. can't be at room temperature, so now doubts arise about how the Korean team achieved it.
It is zero resistance, yet they did not include the essential part.
The paper should be published, so everyone is waiting for its core paper. Now there's suspicion, looking at this chart, that the precision of their measuring instrument is not sufficient. What does that mean? It can't measure very small resistances, so it assumes none exist. No, but yes, it's very famous indeed, so now the Korean Superconductivity Society is requesting the Korean team to provide samples. The society wants to review them, and the Korean team has agreed to provide samples, but they said they need to wait until the paper is completed before providing the samples. However, they didn't specify when they would provide it. As a result, the Korean Superconductivity Association immediately stated that they do not support this, and now refer to it as a room temperature and pressure superconductor. They expressed doubt, and as soon as the Korean Association expressed skepticism, the Korean research team promptly issued a statement saying they would provide samples in 6 months. Moreover, none of the individuals whose names appear on the Korean team's papers are accepting interviews. Even if 1 or 2 people have accepted written interviews with the media, they only emphasize that there are no issues with their research, and the content they discuss is all written in the papers. They do not provide any commentary on more practical situations. The actual situation is unclear. Many suspect 2 possibilities. One is that the Korean team might be involved in stock price manipulation. Oh, when they released this news, the stock market fluctuated significantly. Initially, when the good news came out, all traditional industry stocks plummeted and your concept stocks soared. Now it's being said that this is a bit suspicious because the concept stocks dropped sharply while the traditional stocks bounced back. So if you have concept stocks, you can just make any statement and in the end it's verified. Even if it's not correct, you would have already made your profit. They might be suspected of wanting.
Affecting stock prices, the most affected shouldn't be.
Is it those traditional industries? Yes. This means the second possibility is that this LK-99 might be real, but before it was published, it faced strong suppression from traditional industries. That's why after they published the paper, they have now gone silent and don't dare to talk about it anymore. It's because it would greatly affect the interests of vested groups. Right? When this comes out, many things become unnecessary. If I make batteries, my factory might go broke. Exactly. I've been making wires for ages. You inform me that we will not require it in the upcoming year. It is reminiscent of when they claimed automobiles could operate on water. Didn't that individual vanish as well? Indeed, it evokes that sort of sensation. Thus, the Korean team presented a sample, but it remains uncertain whether the outcomes are genuine or fabricated at this moment.
The paper already mentioned what it was synthesized with, but it said...
It's vague.
The details miss the most crucial, possibly the most core thing, which is the lead sulfate and copper sulfide.
What else could be added? Maybe include more substance, like vinegar.
The information just erupted.
It's definitely the most important. He didn't.
Yes, exactly, so I think we can really wait a bit for this matter. It's something worth waiting for, and if it turns out to be true, it would be amazing. It would elevate human civilization to another level. This is amazing. Our lives will undergo a big change starting today because of this.
Which industries would be impacted if it becomes widely used? Then we can adjust early.
This rice noodle roll, if superconductors are realized, aside from the fields of power transmission and storage and maglev trains, the most likely application areas also include the computer field. Our current computer chips all require cooling.
Understood.
It affects its performance, but if you use a superconductor, it doesn't dissipate heat, so you can make it as big or as fast as you want, right? Your computer could be made thinner without needing space for a fan. Also, superconductors are one of the core technologies of quantum computers, which is quite scary. If artificial intelligence uses quantum computers, wouldn't humanity be doomed, right? And then there's nuclear fusion technology. Superconductors are a core technology for nuclear fusion, so they are a core technology for many singularities. What do you think?
If it is indeed true,